Okay, so today we're diving into something pretty cool, like getting robots to move around.
Right.
Not just like in a simple environment, but like really complex places.
Yep. The kind of places where,
Yeah, like imagine a busy warehouse or a crowded street.
Exactly. Those are exactly the scenarios.
Where it gets really tricky.
Yeah, absolutely.
And there's this paper that caught our eye, right?
Oh, yeah. This one's fascinating.
They've come up with this, well, they call it a hierarchical reinforcement learning architecture, which sounds really complicated.
It is, but in a really elegant way.
Okay, so break it down for us. What's the gist?
Well, it's all about how you tune the parameters that a robot uses to plan its movements.
Parameters, like what kind of parameters?
First, think about things like how fast the robot should go.
Okay.
Or how much space it needs to keep around obstacles.
Right, so it doesn't bump into things.
Exactly. Now, traditionally, these parameters are kind of set in stone beforehand.
Like you just decide, okay, the robot's maximum speed is this, and that's it.
Pretty much, yeah.
But the problem is...
The real world is messy. Things change constantly.
Yeah, you can't predict everything.
And that's where this paper shines, you see. They use reinforcement learning to adapt these parameters on the fly.
So the robot's like learning how to navigate better as it goes.
Precisely. And that's what led them to snag first place in that barn challenge.
Oh, yeah, I heard about that. That's a pretty big deal.
Absolutely. It's a benchmark for testing robot navigation algorithms in super tough environments.
So how does this whole hierarchical thing work? Is it like layers of decision-making?
Yeah, you got it. It's like they have this system with 3 levels operating at different speeds. You have the parameter tuning happening at a slower pace, like once per second. Then you have the planning itself, which runs 10 times faster, so 10 times a second. And finally, the really rapid control adjustments happen at 50 times per second.
Wow, so it's constantly tweaking things to stay on track, and they're using RL for all of this.
Yeah, and not just any RL. They use something called TD3, or Twin Delay Deep Deterministic Policy Gradient, which is ideal for handling the continuous actions we have here, like smooth changes to speed or those parameter adjustments.
So let's dig into this a bit more. Like, what's the big problem that they're solving with this whole approach?
Well, think about it. If you tell a robot to move from point A to point B,
right,
it calculates a path.
Right, like a route.
And then it tries to follow that path.
Makes sense.
But real-world robots, they aren't perfect.
Right, they have limitations.
They might slip a little, or there might be unexpected obstacles.
Yeah, or maybe even just slight variations in the terrain.
Exactly. So what happens is the robot deviates from that perfectly planned path.
And that throws everything off.
Exactly. These deviations are called tracking errors, and they basically mess up the learning process.
It's like trying to learn from a blurry picture, right?
A perfect analogy.
Yeah.
So this paper addresses that by creating this clever feedback loop.
Okay, so instead of just blindly following the plan,
the robot is constantly checking, am I where I'm supposed to be? And if not, it makes adjustments.
so it's like a self-correcting system.
Precisely. And that's where the hierarchical structure comes in. The slower top-level layer sets the overall strategy, like deciding on the maximum speed or how much space to give obstacles. But the faster, lower-level layer is making those split-second adjustments to stay on track. And they're all learning and improving together.
Okay, I'm starting to get the big picture here. Yeah. So how did they actually train all these different components? It sounds incredibly complex to get them to work together seamlessly.
Well, that's where their iterative training framework comes in. Instead of trying to train the entire system at once, they break it down into phases. First, they freeze the control strategy and just focus on training the parameter tuning policy. Then, they hold the parameter tuning constant and optimize the control strategy. And they go back and forth, kind of like refining each piece individually before putting the whole puzzle together.
That's clever. It's like fine-tuning the engine and the steering separately before taking the car out for a spin.
Exactly. And for the training itself, they cleverly represent both the parameter tuning and the control compensation as Markov decision processes, or MDPs. You're probably familiar with these.
Yeah, the good old state action reward framework.
Exactly. So for the parameter tuning, the state is all about the robot's local environment, which they represent using LiDAR readings.
Right. LiDAR is like that laser-based sensor that gives you a 3D map of the surroundings.
Exactly. But raw LiDAR data can be super messy, so they use a VAE, a variational autoencoder, to kind of compress that information into a more manageable form. The action space for this policy is the set of parameters we talked about before, things like speed and obstacle clearance. And the reward function is designed to encourage the robot to reach the goal quickly while avoiding collisions.
Makes sense. So what about the controller? What's its MDP like?
This one's a bit more involved. It operates within a fixed-length MDP, with each episode lasting a tenth of a second. The state for the controller includes, of course, the latest LiDAR readings, but also things like relative trajectory waypoints, which are essentially points along the planned path. It also includes the current time step within that short episode, the robot's current position relative to the planned path, and its velocity. All of this helps the controller make those super fast adjustments. The action for the controller is the predicted feedback velocity, which is added to the planned velocity to correct for those tracking errors. And the reward function, similar to the parameter tuning policy, focuses on minimizing tracking error and avoiding collisions.
So it's like the controller's constantly saying, okay, I need to nudge the velocity a little bit this way or that way to stay on course.
Precisely. And that's why having it output just the feedback component rather than the entire velocity command makes the learning process much more stable. It's a smaller, more focused problem to solve.
Okay, I see. So they've got this elegant hierarchical structure. They're using a robust RL algorithm, and they've got this clever iterative training scheme. But did it actually work? Let's talk about the experiment.
Oh, it worked. And how? They really put this thing through the ringer. First, they tested it in the barn challenge simulation environment.
Which, as we mentioned earlier, is a pretty tough benchmark. What kind of robot and setup did they use for these simulations?
They went with the standard Jackal robot model, a popular choice for research. It's equipped with a 270-degree LiDAR for sensing its surroundings, and it can hit speeds of up to 2 meters per second. They also use the Robot Operating System, or ROS, for all of the software infrastructure and the well-established Move-based navigation package. Within Move-based, they use Dijkstra's algorithm for global path planning and the Timed Elastic Band, or TEB, planner for local trajectory optimization. Importantly, the TEB planner has those parameters that their system was dynamically tuning, things like maximum speed and obstacle avoidance weight. They use the ROS Dynamic Reconfigure client to adjust these on the fly based on the output of their parameter tuning network.
Okay, so a pretty standard setup to ensure a fair comparison against other methods. And what were the key findings from these simulated experiments?
Well, first off, their hierarchical approach absolutely crushed the baseline TEB planner, which only achieved a 70% success rate in the barn challenge with an average completion time of 26.7 seconds. Just adding the parameter tuning alone boosted that to 84% success and cut the time down to 13.2 seconds.
Wow, that's a huge improvement. And then what happened when they added the RL-based controller on top of that?
Well, that pushed the success rate even higher, to 90%, with a slight decrease in completion time to 12.9 seconds. But the real star was their full system with the iterative training. That bad boy achieved a whopping 98% success rate and blazed through the courses with an average time of just 10.2 seconds.
Okay, so it's clear that both the hierarchy and the iterative training were critical for getting the best performance. Did they compare against other parameter tuning methods as well?
Oh yeah, absolutely. They went head-to-head against some of the leading approaches out there, like APPLR and APLE.
And how did they stack up?
Well, their method differed in a couple of key ways. First, they used those compressed LiDAR features from the VAE instead of the raw data. Second, they tweaked the reward function to emphasize global progress towards the goal and let the lower-level controller handle obstacle avoidance. And the result? They blew the competition out of the water. Figure 6 in the paper shows this really clearly. Their method consistently outperformed these other techniques across all the barn challenge scenarios.
That's impressive. So it seems like they really nailed it in simulation. But of course, the real test is how it performs in the real world. What did their real-world experiments show?
Right, because we all know simulation can only take you so far.
Exactly. So did this fancy system actually work on a physical robot?
Well, they tested it on a real Jackal robot in 8 different real-world environments. 4 of these were indoor office-like spaces, and the other 4 were corridor environments, all distinct from the barn challenge scenarios. And guess what? The off-the-shelf TEB planner, the one that didn't have any of their fancy learning, completely failed in all 8 environments. It just couldn't handle the complexities of the real world.
Ouch, that's rough. So parameter tuning to the rescue?
It helped, but not consistently. In some environments, it managed to navigate successfully, but in others, it still struggled. But their full system, the one with the hierarchical structure, the RL-based controller, and the iterative training, That thing aced every single test. It achieved a perfect 100% success rate across all 8 environments. And not only that, it had the lowest average tracking error and the fastest average completion times compared to all the other configurations they tested.
That's amazing. So it seems like they really cracked the code on robust and adaptable robot navigation. What are the key takeaways from all of this?
Well, I think there are 3 big ones. First, this hierarchical architecture, with its different operating frequencies for parameter tuning, planning, and control, is a really powerful idea. It allows the system to handle both long-term strategic decisions and split-second adjustments in a very elegant way. Second, that RL-based feedback controller is a game changer. By focusing specifically on minimizing tracking errors, it significantly improves the robot's ability to follow the planned path accurately, even in the face of real-world uncertainties. And finally, that iterative training approach is crucial for getting all these different pieces to learn and work together effectively.
It's like they've created a system where the whole is truly greater than the sum of its parts.
Exactly. And the results speak for themselves. This approach is a big step forward in creating robots that can navigate reliably and efficiently in the messy, unpredictable real world.
So what are the broader implications of this research for the field of robotics and AI?
I think it has the potential to really transform how we think about autonomous systems. This combination of model-based planning and data-driven learning, along with this explicit focus on the connection between planning and control, is a blueprint for creating more robust, more adaptable, and ultimately more intelligent robots. And it's not just limited to navigation. These ideas could be applied to a whole range of robotic tasks like manipulation, grasping, and even human-robot interaction.
It's really exciting to see these kinds of breakthroughs happening. And it leaves us with a question for all of you listening. How else can we apply these principles of hierarchical learning and adaptive control to other complex problems in robotics and AI? Are there other areas where separating high-level decision-making from low-level execution could lead to significant performance gains? And how can we design systems that can learn and adapt to constantly changing environments and unexpected challenges? These are the kinds of questions that are driving the future of intelligent systems, and we encourage you to explore them further. Thanks for joining us for this deep dive.